Continuing onward, we're going to look at how to calculate the error for the output of a neural network or a support vector machine, or really any type of machine learning construct where you're presenting an array of input and expecting some sort of an output. This is supervised training. You're going to have some sort of ideal output, and we're going to compare the ideal output from the actual output of the machine learning construct. First, let's get some sample data that we can deal with, because this is supervised training. For supervised training, you're going to have input and ideal. The input, we're going to use the exclusive OR yet again. And we're going to have some sort of ideal output for each of these. And exclusive OR, when they're the same, it's 0, otherwise it's 1. This time, though, we're going to have an actual. And the actual is going to be what the neural network actually outputted. And this could be really anything, because the neural network is usually initially started with random weights. So we're going to have the actuals. I'm just going to make them up for now because it really doesn't matter. We're going to calculate. We're going to assume they're not real close to what we really wanted. So we'll do 0.2, 0.3, 0.4, and 0.5. So we started out with some sort of random weights in the neural network, and this is what the neural network is actually giving us back. Now, what we need to do is we need some way of comparing this ideal and the actual. There's several ways that you can do this with a neural network. We're going to look at really 3. And these 3 different ways, the most common way probably is the mean squared error. Mean squared error, or the MSE. That's the most common. Another one that is somewhat common is called the root mean squared error. Which is abbreviated usually RMS, or perhaps RMSE. And then the third one that is really not all that common, but it's used with a training technique called QuickProp, which is sort of like backpropagation, except it has some enhancements to it. And it's usually called the arctan error. So these are all of the ways that we can potentially calculate the error. They all work relatively similar. You're going to, in mean squared error, you're going to have, for all of these, you're going to have a number of samples. For this one, you have 4 samples. Now, some neural networks will have more than one output neuron. If there were two output neurons instead of just the one here, you would have twice the number of samples because you would have 4 additional actuals, so you would have actually a total of 8. So it's important to remember how many samples you actually have. Very, very often a neural network has a single output neuron, but they can definitely have more than one. So the way that we would calculate this is you would want to take the input, or the ideal, minus the actual. So the input, or the ideal one, minus the actual one, gives you sort of a delta. And you are going to then add that to your next sample. Let's ID 2 minus actual 2 plus dot dot dot, however many of these you have, plus ideal n, because you're going to have n number of these, minus actual n. Almost forgetting one very important part. You square all of these. So each of these differences you square. That will eliminate any differences between positive and negative numbers. And then you take this whole thing divided by n. I almost didn't leave enough space here. But, so it's very similar to a average or a mean that you might already be used to dealing with. So you're going to then, that then gives you a final resulting number, and that is going to be the mean square error. Now, root mean square error, you really take that entire thing then. I'm not going to rewrite the whole thing, but you just take the whole thing and then you feed it back through a square root. Arctan error is very similar to these, but a researcher named Fallman wanted to penalize the neural network more for errors that were bigger errors would be counted more. So you can see this exaggeration is done using a arctan function. Let me show you what an arctan function actually looks like. Oops, there we go. That's an arctan function. And you can see as it gets further from the origin, the error would be exaggerated more greatly. The way we can do that is the arctan error works on each of these individual samples. So it would be more like arctan squared of input 1 minus actual 1. And that's just saying square the result of the arctan. And it would be really just like mean squared error. You would add in the rest of that, and then you would finally divide the entire thing by n. And like I said, it's just like that one up there. Except that would be arctan squared. So I'm not going to draw the entire thing out, but like I said, it is exactly like the rest of the mean squared, except each of these you're taking the arctan and then squaring it. Okay, let's look at what the differences are. The differences are going to be 0.4, 0.04 actually. Zero point 49, 0.36, and 0.25. Oh, and I should state, this is not just the difference, this is the delta squared. I went ahead and worked this all out in Excel. So those are those values, the delta squared. If you sum those all up and divide it by 4, because there's 4 of these total, it gives you a final error of 0.285, which would often be represented as 28% or 28.5%. That is the MSE, the mean squared error. If you wanted to calculate the root mean square, you would simply square root that entire thing, and that would be 0.533. So that is, again, like I said, I am basically taking the difference of those two, squaring it, and that equals that. That's how I'm calculating each of those values. I'm not going to take you through calculating every single one of those. YouTube doesn't give me enough time to do that. But then you're left with each of those. If you were to calculate the arctan error of it, that would actually be 0.2297. 0.2297, depending on how accurate you want to go with that. So that would be the arctan. So you see, really, the 3 different error calculation means that you have here. And the different numbers that you would get back. I'll probably do another video in the future analyzing some training sets and why you might choose one over another. Usually, the one that you're going to want to use, and the one that most examples on neural networks make use of, is the mean squared error. The arctan error will exaggerate greater errors, but you can see it's relatively similar to the mean squared error. So if you want to punish larger errors more so, you'll use the arctan. The root mean squared error adds in the radical at the end to sort of, and it gets into more statistics, which I'll explain when I do a video where we explain the differences between those. But it attempts to sort of neutralize the squaring that was done here to account for the fact that some errors are going to be negative, some errors are going to be positive. So whenever in doubt, use the mean squared error. If you're using QuickProp, which I will probably do a video on as well in the future, that's just another training technique, then you'll want to use arctangent error.